Section 4 is on specific heat. So with the two balloons, the air balloon pops real quick because it doesn't take long to heat up the balloon and the air inside of it. Okay, now you don't have to heat all the air inside the balloon, just a little bit of it right next to the balloon and pop. Now, the water balloon, however, you put the flame there and the water is absorbing all that heat. We're adding heat to it, but the water is just taking it in and taking it in and taking it in, and it just keeps on taking it in, and the balloon cannot get hot because the water is so quickly absorbing all that heat. So, what's happening to the little molecules in the water? They are speeding up, but it turns out that it doesn't take the same amount of heat to speed up all molecules. Some of them want more to speed up, depending on their mass. Alright? Some of them need more to speed up than others. There's a table in your book on page 421. Take a look at that. Each molecule within a specific object they would all be the same mass. Yeah. Okay. If it's a common substance. All right. So that tells you, that table, notice the units, it says specific heat, and it's in kilocalories per kilogram degrees C or joules per kilogram degrees C. What that is the specific amount of heat you would have to add to a kilogram to make it go up 1 degree C. Notice water, which is over there on the right-hand side, liquid water, 4,186 joules of heat to raise 1 kilogram of water, which we probably have in that balloon, 1 degree Celsius. Okay? Now, I don't know what it is for air, but for oxygen, 0.15 kilocalories per kilogram, so liquid water is way more than that. Alright? Now look at aluminum and say iron or steel. If you got aluminum, it's 900 joules per kilogram, and then you've got iron that's 450. If I put a kilogram of iron and a kilogram of steel on my stove and I turn them both on high, which one heats up faster? It is the iron or the steel. Alright? The aluminum would take exactly twice as long, because I need twice as much heat just to go up 1 degree. Twice as many joules to go up each degree, so it would take exactly twice as long to heat up the aluminum as it would the iron or steel. Okay? Now, formula for this is pretty simple. Just Q, which is our heat added, is equal to the mass times the specific heat, that's a C, times the change in temperature. I have no idea what just happened there, but we are going to cut it out. Alright. Yes, the specific heat is the constant in the table. Is that?
That's a good observation there, Bo.
Taking out parts of my word, isn't it? Wow. Alright. Now I gotta go back over here and click the pen. Technology is wonderful. Specific heat. What is Q? Q is your heat. That's how much energy we add to it. in order to raise the temperature or take away if we're lowering the temperature. M is the mass. Now, delta T is the change in temperature. It's really... No, it's temperature. It's temperature. It has to be, because it's a change in temperature, it has to be in either Kelvin or Celsius. Celsius going from 0 to 100 is a change of 100, right? Well, Kelvin would be going from 273 to 373 for the same thing, which is still a change of 100. So as long as it's in Celsius or Kelvin, you're all right. But then all that last stuff had to be in Kelvin. So on the test, if you're in doubt, convert to Kelvin. You're not going to hurt yourself ever. Okay? All right. Let's what? M is your mass. See, look, guys, your specific heat is joules per kilogram degrees C. Joules per kilogram degree C. Now, that means how much heat is required to raise a kilogram a degree C. That's what your specific heat is. How many joules of heat for each mass of a kilogram and for each degree. If you multiply how many kilograms you have and how many degrees C you go up times this number, you get how many joules that it takes to do that. Alright? Look at number 1 on 439. 439, do number 1 real quick. Should be easy.